This is a video on thermal energy standard number 3, and standard number 3 says the size of objects in contact affects the amount of energy transfer between them and the amount of temperature change. So when we look at two examples from the sim, we have a very small sample, so sample A, and sample B, which is a large one. There are much less molecules in sample A, or many less molecules in sample A than there are in sample B. And I know this because remember that the dots represent molecules. When we look at those two samples or objects, the samples are currently at the same temperature. So even though sample B is much bigger than sample A, they're at the same temperature. But when we look at the thermal energy in those samples, the thermal energy in sample A is much lower than the thermal energy in sample B. Sample B has a higher thermal energy because it has more molecules. So even though these samples are at the same temperature, sample B has a higher thermal energy. This should remind you of the article we read where it compared a bowl of soup to a mug of soup. And it talked about a brother and a sister eating soup, and the sister putting ice into the bowl, into the mug, and in the mug, the soup got really cold, and the bowl was nice. And then also when they put the mug and bowl into the microwave, the mug got really, really hot where the bowl was just right temperature. This story reminded me a lot of Goldilocks and the Three Bears. So what we can learn from this article was that the bowl of soup on the left is the same temperature as the mug of soup on the right, because both are made of molecules moving at about the same speed, and we can see that by the speed lines, or the little tails on the molecules. So they have the same average kinetic energy, so they have the same temperature. However, because the bowl of soup is made up of more molecules, it has a higher kinetic energy, or its thermal energy. And we annotated this article, and we really wanted to stress that paragraph that thermal energy is the total kinetic energy of molecules in an object or material, and it's not the same as temperature, which is the average kinetic energy. And we asked you to put the word thermal energy into your lab notebook, reminding you that thermal energy is the total kinetic energy of all the molecules that make up a sample. We showed you this graphic. So when we look at all of these little molecules moving and we add up all of them moving, that is thermal energy. Where if we just average how much they're moving, that is temperature. So I really hope you guys remember these slides because I just thought this was so much fun. So we have our hot chocolate versus a frozen iceberg, and you're asked the question, which has more thermal energy? Okay, so let's just start with which one has a greater temperature. Now I hope most of you are saying the hot chocolate has a greater temperature. But then the question was which one has greater thermal energy, because remember, they're not the same thing. We compared this to sound energy. So we have one crazy Sounders fan screaming their lungs out versus all 70,000 fans at CenturyLink Field snapping their fingers. We asked which one has more sound energy. Now I hope that even though this crazy guy screaming his lungs out there looks real fun, you guys realize that if you had 70,000 fans snapping their fingers at the same time, that'd be a lot louder. And we related that to the mug of hot chocolate. So the mug of hot chocolate is warmer. It has a higher temperature. It's like the screamer, that single scream is loud compared to one snap. But when you have all of the snapping together, that would be like all of the kinetic energy of the molecules together. So the total of all of those is greater. So that means that our iceberg has more thermal energy, even though it has a lower temperature. And then we asked you to jot a couple notes in your lab notebook. We said that all matter is made of atoms and molecules, and atoms and molecules are in constant random motion. They're always moving. And thermal energy is all the kinetic energy due to the random motion of those particles. So that leads us to scientific principle number 8. For things at the same temperature, the thing with more molecules has more total kinetic energy or thermal energy than the thing with fewer molecules. Okay, so let's look at these two objects. Remember that the orange or yellow dots, those are actually energy cubes. Those are not molecules. The molecules are the big circles. So object B has a energy cube in each of the molecules. Therefore, it has a total kinetic energy or thermal energy of 2. But it has an average kinetic energy or temperature of 1. Object A has 5 in each molecule, so therefore it has an average kinetic energy or temperature of 5, but when we total that up, that would be 5 times 6, so 30 for its kinetic energy, for total kinetic energy, which is thermal energy. And we had this fun demonstration where we had two systems, system X and Y. Both had a cup and a bowl. In system X, the cup had less water in it than system Y. The water temperature started at the same, but over time, we watched what happened to the temperature of the systems. And I just want to thank Ms. White's third period for recording data and having that with us to share here. So what we see is that over time, cup Y, the temperature over time goes down. So yeah, that's started at 61, it goes down to 30 or to 25. The bowl goes up. Okay. But then if we look at what's going on in system Y, oh, and I see an error here, third period. I'm just kidding. That should say bowl Y right there. So in cup Y, the temperature goes down, but it does not go down as much as it did in cup X. And then bowl Y increases temperature, and it increases temperature more than bowl X did. Well, remember that cup Y was larger, had more water molecules in it, so there was more energy available for transferring. And an important thing to remember is that to reach equilibrium, energy has to transfer, so the total kinetic energy of both objects is divided among the molecules of the system. So that means at equilibrium, the molecules of both objects have the same amount of kinetic energy. So the total kinetic energy of the objects might be different, but their temperature or average amount of kinetic energy is going to be the same. Which brings us to scientific principle number 9. At equilibrium, the average kinetic energy or temperature of the molecules in the system is the total kinetic energy evenly divided by the number of molecules in the system. So to find out the equilibrium temperature, we have to take all the kinetic energy in the molecules and divide that by how many molecules we have in that entire system. Scientific principle number 10 says, when a thing gains or loses energy, the energy gained or lost is divided among all the molecules in that thing, or that thing could be also replaced with system. Okay, so we're going to take a look from the modeling tool. So you guys were given this modeling tool, and hopefully that we're realizing that sample B, the sample B is at a higher temperature than sample A. And most of you, I am assuming, would go ahead and put an arrow going up. Now, the tricky part is thinking about what the temperature for time 2 would be. When we take a look what that ends up being, some of you, I think, are surprised that over here at time 2, we see the temperatures all being 2. But look how many molecules there are here. There's only 5 molecules down here, whereas there's, how many is that? 15. up here. There's way more molecules in sample B, or sample A, than there are in sample B. So the energy that transfers from sample B has to spread out over all of those molecules. And when it spreads out over all of those molecules, we have a lower kinetic energy in all of those molecules. This modeling tool is different because we can see that we have 15 molecules in sample D and 15 in sample C. So sample D has a higher average kinetic energy or temperature, so the energy is going to transfer to sample C. But when we look at what happens over time, hopefully this makes a little more sense that at time 2 we have 3s for sample C and D because the molecule or the energy is spread out over the molecules, and there is more molecules in sample D, so there could be more evenly spread out energy. Okay, I went into the sim because I want to just illustrate a couple of concepts. So I have two sides objects, and I'm going to make the larger object warmer, and I'm going to go up to 47.7. I'm going to put these. Let's just go up to 100. What am I thinking? Let's go up to 100. Okay. So when I have this up to 100, I'm going to go ahead and put them together, and our energy is transferring to the warmer to the cooler, and I sped it up, so hopefully we're going to get ourselves to equilibrium pretty quickly. And it looks like our equilibrium temperature is going to be about 81.2. Now I'm going to go ahead and reload the sim, and then this time, yes, I'm going to still do a small, and I'm going to add a large one again. And now I'm going to make the small one up to 100. Okay, and I'm going to go ahead and turn on those toggles there. Okay, so this time, because sample A is warmer, we're going to have energy transferring from sample A to sample B. Let's go ahead and see, though, what the equilibrium temperature is. Okay, I did speed it up, I promise. So now we're getting towards equilibrium here, and it looks like our equilibrium temperature is going to be 43.8. That is significantly different than the last sim. So when we had let me pull you apart there. Oh, it doesn't want to go apart. When we had a small box that was moving really, really fast, so really warm, yeah, it still transferred energy, but the equilibrium temperature was much lower. So the amount of energy that small object transferred was actually a lot compared to the large object. Because the large object was so big, it had a lot of energy to be able to transfer, and that spread out over a small amount of molecules. Because in our last sample, let me just go ahead. I know you guys are going to get on me about redoing this, but in our last sample, when we had this large and the small, and we move this up, and yeah, I'm getting it hotter. Here we go, here we go, here we go. The energy in sample B was transferring over to many fewer molecules. So to get those molecules up to speed was a lot easier, actually. This standard has 4 different scientific principles that we talked about in class. Principle number 7, the molecules of a system will transfer energy until the system reaches a stable state known as equilibrium, in which all the molecules are moving at about the same speed. We've covered equilibrium in previous videos. For number 8, for things at the same temperature, the thing with more molecules has more total kinetic energy or thermal energy than the thing with fewer molecules. 9, at equilibrium, the average kinetic energy, so the temperature of molecules in the system, is the total kinetic energy or thermal energy evenly divided by the number of molecules in the system. And number 10, when a thing gains or loses energy, the energy gained or lost is divided among all the molecules of the thing. Okay, so we're going to quickly go through an example assessment question. So we have a graphic here where we have two things of plastic, as stack 1 and stack 2. We can see the difference in stack 2, that the top plastic, look how much bigger that is. There's more molecules in that. Now the molecules are moving the same speed as in the top plastic 1, but there's just more molecules. So your question is asking, construction worker is transporting pieces of plastic in 2 stacks. In stack 1, both pieces are the same size. Stack 2, the bottom size is the same as it is in stack 1, but the top piece is larger. Okay, so we should automatically see that energy is going to transfer from the bottom to the top. Okay, so which of the top pieces will be cooler and why? Okay, so first we need to think about how many molecules there are. So there are way more molecules in top plastic number 2. There's just a lot more than there is in top plastic number 1. So the bottom plastic, it's going to have to transfer a lot more energy to get the top plastic to equilibrium. Whereas over here, stack 1, they're going to have to transfer less. So we know stack 1, the top plastic is actually, when it reaches equilibrium with the bottom, is going to be warmer than it is in stack 2. So we should be able to cross out D already. We should be able to cross out C already, and then we're left with B and A. A says the larger top plastic pieces will be cooler than the smaller. It's started with more total energy, so less energy had to transfer for both pieces in the stack to reach the same total energy. And B says the larger top plastic piece will be cooler than the smaller because the energy that transferred to it was spread out over all molecules. So let's look at A, at the second sentence. It says it started with more total energy. Okay, so less energy had to transfer for both pieces in the stack to reach the same energy total. So while the top piece did start with more total energy, that part is true. Because there are more molecules, more energy actually from the bottom had to transfer up. So that A cannot be correct. So therefore B has to be our correct answer. So if you have additional questions on Progress Build 3, please make sure you're talking to your teacher, and best of luck on your retake.